Good day, and welcome to our webinar presentation. My name is Adam Harris, Managing Director here for C-Therm Technologies, and really pleased to welcome you to our presentation today. We've been running these educational webinars every week over the last 6 months as a replacement for some of the conferences and different academic and other initiatives we were involved with, which required a lot of travel. Of course, in the current pandemic situation, we're limited to these types of engagement, but the benefit is we get to connect with a much broader range of folks from all over the world, and are really pleased that you could take an opportunity to join with us today. We know that your schedule is packed and you're balancing a lot of different professional and family commitments. So we won't delay, and we'll get started right along here. So today's feature presentation is on testing the conductivity of different types of geological samples that come in a lot of shapes and formats and states. And we'll speak to how to characterize them. There's a variety of different methods based on what type of sample you're dealing with in geological terms. So we'll address a little bit how to measure it. We'll talk about why the data is important. We're going to feature some different application content from some different resources of the results generated with the C-Therm equipment, and we'll try to bring this all together in a nice presentation. I'm going to be introducing the star of our show here shortly. Sarah Ackerman is the head of our application lab and has curated this webinar presentation on geology, and I'll be introducing her shortly here. In terms of an agenda, the presentation will run for approximately 60 minutes, and we've reserved some time at the end for a Q&A session. We are recording, and this will be posted on our website. You'll automatically receive a link to the recording. So if there's any part that you wanted to rewind on and listen again, or dial in a little bit more on, you certainly have that option. You can certainly share this with other colleagues who are unable to be with us today. Other than that, I want to take note that we've got a few folks helping us out today with this webinar. Rosa Chen is our regional manager for China and other parts of Asia. She is helping us moderate the session and has helped organize it. I really appreciate Rosa's help with this. She does a great job. So you'll be seeing different messages as we go in the chat box through the presentation. Stuart Hillhouse is our marketing manager. He's also played a strong role in getting these webinars organized. I think he's online with us today as well, and I very much appreciate his assistance also. So with that said, I'm going to provide a little bit of background on C-Therm Technologies and the capabilities that we introduce here as part of the solution for characterizing different samples in the geological space. And then I'm going to quickly pass this on to the expert, which is Sarah Ackerman, who will take us through some different curated material specific to the application space. So to start with, who is C-Therm Technologies? I know a number of you know us quite well. I see lots of friends on the registry here, but I see several names that we may not know as well. So welcome. C-Therm Technologies, we're very much niche experts. So we don't have a really broad product line in thermal analysis and broader instrumentation. What we do is very, very focused. What we do, we're the best in the world at, which is in the measurement of thermal conductivity. We've advanced the characterization of thermal development and improvement of a variety of transient methods for thermal conductivity. We've won several awards over the years, including the top technical award for innovation in Canada. We are a Canadian company. The original inventor of one of the methods we're going to feature today, the Modified Transient Plane Source technique, is a unique single-sided sensor, won the inventor the Manning Innovation Award. This is a $100,000 cash prize for the most significant technical achievement in the country. That was a few years ago. We've won several other awards, including our R&D 100 award and several other companies such as developers of Polaroid film, anti-lock brakes, the automated banking machine, a smartphone, prestigious class in terms of technical innovation. So we're pleased to share with you today that technical innovation and that capability we bring in thermal conductivity. Our goal in life, our raison d'etre, is to make it simpler, more accurate, more representative of the types of application conditions in which you're looking and seeking for good representative thermal conductivity data. And particularly in geology, where we may deal with higher pressure conditions, a variety of temperature, humidity, atmospheric conditions. These are all easily replicated, and our sensors integrate very well in these different types of environments. We have, for example, a line of high pressure cells, which is very novel in its offering to characterize some of these conditions. I'll speak a little bit more to some of the flexibility as we progress in the presentation. Quick overview of our product lineup. So the product in the middle is our Trident thermal conductivity instrument. This is a research grade instrument. It is our most powerful instrumentation for thermal conductivity measurement. It brings together those three most prominent transient methods for thermal conductivity: the Modified Transient Plane Source, which we've invented and patented, the only single-sided sensor technology available; the Transient Line Source needle probe, that's the sensor in the middle there in front of the pyramid. This is sheathed in stainless steel, very robust, great for either very sticky situations like a melted bitumen type sample, or in other industries, a polymer melt, anything that might bond or stick to this other sensors and damage them. The stainless steel sheathing on the TLS provides excellent robustness. And then you have the yellow sensor, which is a transient plane source sensor, sometimes called a hot disk style sensor. This sandwiches in between two samples, no need for a contact agent, and really the powerful capability that this brings is oriented towards a more experienced user that can push out the capabilities further in terms of what can be measured. So great for more challenging situations like measuring anisotropic samples, thin films, slab materials. Also really good on rougher samples. So it's the combination of these methods in one toolbox in terms of thermal conductivity capability. Trident has become our most popular product very quickly. It was launched to great fanfare last year and is by far our most popular product. To the left is really a solution that's oriented towards researchers who are struggling for budget. The TC kit, thermal conductivity kit, is paired typically with a Keithley source measure unit, a laptop. It provides the software for the data acquisition and regression analysis. It provides a TPS sensor, reference material, and you can easily put that package together and establish a basic capability to measure conductivity up to 65 watts per meter Kelvin. Now, this is used in a lot of different undergrad teaching experiential labs. There are some sample exercises available on how this can be incorporated into coursework. But it's also great for bootstrapping organizations, startups, hobbyists, and folks who are maybe because of the pandemic looking to work more from home and want some basic measures, to mirror what they have in the lab or elsewhere. So this is a really economical offering. I think Rosa will probably drop in a link to where you can find out more information on the TC kit. It can be purchased online. We're listed on the Shopify platform. So very simple, easy process for the TC kit. On the far right is a product that doesn't necessarily have a whole lot of relevance from the audience today, but it's really popular in consumer goods and apparel, particularly in textiles and fabrics. Think of different sporting apparel groups. It's a device that measures the touch property of materials. It quantifies how warm or cool it feels to the touch. There is a little bit of application space with ceramic tiling and some of these types of different tiling that I've seen this instrument applied. For example, there was a group in Mexico that was using it to profile the feel of different ceramic floor tile. So when you walk on the floor, one of the challenges is as it gets cooler out, it feels cold. You get out of the shower, it's not as comfortable. Lower the effusivity of the material, so it has a warmer feel, and that's what we quantify, is that warm feel or cool touch with this. So I know of one case, a researcher in Mexico that was playing with the porosity structure of the ceramic tile and adjusting and tailoring the touch property in doing so. So maybe a little bit of a tangent, but if you're interested in more information on the TX Touch Experience platform, we'd certainly be happy to provide that. You can enter that in the chat box. So we'll feature Trident quite heavily in today's presentation because all three methods are relevant in different geological samples. I know Sarah is going to go into these in significant detail, so I'm going to move this along quite quickly. But to take one step back on the motivation and philosophy for Trident, I like using this quote from Abraham Maslow. Maslow, you might remember, a very prolific philosopher, researcher. I remember him from my organizational behavior course. I wrote the hierarchy of needs. Anyways, that's a different topic. But the nice quote here, that when all you have is a hammer, everything looks like a nail. And this just really captures for us the motivation or the philosophy behind what we were trying to accomplish with Trident, which is, in thermal conductivity, there is no silver bullet that one technique or method handles all ranges of materials and scenarios. It's really about having a toolbox available to you, and you select the best tool for the job at hand. So, what we've done with Trident is we've brought together the three most prominent methods for transient thermal conductivity measurement. We've advanced them considerably. We've made them simpler to use. With MTPS, we completely invented the method and patented it. And the other two are our standard ASTM and ISO methods that we've added a significant improvement to and brought them all together in this Trident platform. And that's really what is nicely captured here, is that, let's get rid of the bias that we have to a predisposed solution. Let's bring together the best available tools and make them available to you in one platform. And that's what Trident's all about. These different sensors are on screen. The needle shape is the needle transient line source. It requires the largest volume of material. The Flex TPS is the one in the middle. This is sandwiched in between two samples, rather. Sarah will detail a bit more, I think, the principle of operation, but it is available in different size formats. You would tend to lean towards the larger size format for most geological materials, where you want a larger evaluated volume of material based on the heterogeneity aspects of it. And then MTPS is the one on the left, and that's the simplicity, the best precision and reproducibility, easily measure conductivity for a broad range of materials. You'll see each one of those featured in the work that Sarah will present. A few different accessories that are available with it. Of note, the high pressure cell pictured on screen. So a lot of extraction processes, for example, require us to understand the heat transfer properties under high pressure conditions or high temperature conditions. And our high pressure cell here pictured, this is one version of it. There's different models, can easily integrate in the provided thermal chambers that we offer. And this gives you an ability to really mimic the application conditions very, very closely. So you get really good quality representative data for your purposes. This is the table just of the specs in terms of the ranges. I'll let you read those. The most precise and the most precise technique is the MTPS. TPS, Flex TPS and MTPS have very similar accuracies. The needle transient line source is stated a little bit differently. It's rated to the temperature, and then it drifts out further the wider the temperature range. But you get a good sense of the overall capabilities of these systems and the broad range of ASTM and ISO methods that this platform supports and conforms to. I'm going to pass this over to Sarah here. I just wanted to end with a nice client testimonial. This is from a client of ours more locally here in Atlantic, Canada, Seaforth Geo Surveys, based out of Dartmouth, Nova Scotia, so not too far from C-Therm, which is located in New Brunswick. They take the system out as a relatively portable system on ship, in a Pelican transport case, so it travels very well and is used in their mobile lab. And what they're doing is they're extracting samples from the bottom of the ocean and bringing them up on deck and measuring them quickly in terms of their effective thermal conductivity. The reason this is important to do on ship is because those samples will dry out if you bring them back to shore. And so, the humidity level, the moisture level of the samples has an impact on the effective thermal conductivity. And so for us to have truly representative data, we want to do that as close to extraction as possible. And the nice quote here from David Lombardi. I don't know if David's on the line with us today. He sometimes attends these presentations, but comments on Seaforth Geo Surveys turned to the C-Therm instrument for effective thermal conductivity characterization in our exploration vessels onboard lab. The portability and ease of use of the instrument allowed our technicians to rapidly measure the thermal conductivity of our geological core samples accurately and consistently in a 24/7 operation. As a Nova Scotia-based company working worldwide, we were pleased to have a local made in Atlantic Canada solution for our project requirements. We would recommend the TCI system for any research or screening with a focus on geological and/or in situ applications, and we will continue to utilize it on new exploration missions. So that's a really nice capture from David, and very much appreciated. They do great work in geomapping, and I know Sarah will talk a little bit geomapping and the importance of thermal conductivity in some of our application work. So I've probably taken up more time than I should, and I want to get this quickly passed over to Sarah. So I'm going to stop sharing my slides. Sarah's going to join me on camera here. A little bit of background on Sarah. She heads up our application lab here at C-Therm Technologies. She loves working with clients on challenging thermal analysis, calorimetry, and thermal conductivity issues. She's developed a very successful business here with thermal analysis labs in helping clients with these types of challenges. She is an expert in thermal conductivity particularly, and has been curating these sessions for us over the past 6 months. Always does a great job of bringing together some very relevant, very interesting, complementary kind of different application cases themed around a certain area. And today we're obviously focused on geology. So with that said, Sarah, I'm going to pass this over to you, and we'll let you take it from here. I'll rejoin you on the Q&A.
All right, thanks, Adam, for the introduction. Just load up my slides here. So what we're talking about today specifically is thermal conductivity testing and how it's used in characterizing different geological systems and processes. So I'll start by taking a step back a little bit and talking about what geology itself is. So geology is basically the science which studies the Earth, its composition and structure, and the processes that cause that composition and structure to change over time. You can also apply the same sorts of principles and study techniques to studying different celestial bodies like planets, stars, and exoplanets, which is generally referred to as exogeology. Um, so when we're talking about thermal conductivity, it's important to understand what that term actually means. So thermal conductivity is a material property which is more or less analogous to the electrical conductivity, in that it's talking about how well a material or substance can transmit heat through itself. So if you're talking about a one-dimensional heat transfer scenario, like you see on the slide here, um, the thermal conductivity number property in that direction determines how much thermal energy is going to flow as a function of time, or the rate of the thermal energy flow through the material of a known thickness and cross section when it's exposed to a certain temperature gradient. So that's what gives us the units of thermal conductivity in watt per meter per Kelvin. And when we're talking about thermal conductivity, it's important to understand why it's actually important to the field of geology and to the field of earth science. And in short, it's because heat transfer is really key to those geological processes that cause the earth to change, especially the more dramatic ones. Like, for example, the mantle convection that drives plate tectonics, volcanism, uh, e- eruptive processes like geysers, and also in some of the slower processes that go on, like hydrocarbon deposit formation, as well as I didn't have room to fit it on the slide, but metamorphic deposit processes can be governed by heat transfer and the physics of that heat transfer. In terms of our point of view as humans who may be looking to uh, exploit geological resources, heat transfer is also very important from our point of view in evaluating um, geothermal sites for use in geothermal resource exploitation, as well as in evaluating oil and natural gas extraction processes, especially the non-conventional extraction processes, like, for example, fracking and enhanced oil recovery techniques. So the bulk of the presentation today is going to focus on a technique called the Modified Transient Plane Source, or MTPS technique. The sensor for this technique is seen on this slide in the upper left there. And this sensor is basically a single-sided interfacial sensor, and the active area is that green chip that you see in the center of the sensor area there. Um, so you can see that the sensor has two parts. One is a spiral in the center of the green region. And then on the outer edge, it might be a little difficult to see, but if you look closely, just inside of the red ring, which is a sealant material, you'll see another dark trace. And that's the guard heater. And that's really important to how the modified transient plane source method works and how it can measure not only the thermal conductivity, but also the thermal effusivity, which can be important in terms of evaluating the efficiency of one-dimensional heat transfer, because it dictates the interfacial temperature between two bodies. So when we run a test with a modified transient plane source sensor, uh, what we'll do is we'll fire that sensor spiral I pointed out previously at the same time as we fire a heat pulse to the guard heater on the outside, the guard ring. So those two electrical traces both heat at the same time. It's both done simultaneously. And what that does basically is because the guard heater is heating at the same time and with basically the same intensity as the sensor coil only sees a thermal gradient or a temperature gradient in the direction straight up, or what physicists would call in the direction normal to the plane of the sensor surface. And so what that does basically is ensure that the effective heat transfer is only one dimensional, and we can get at that thermal effusivity value, which sees a lot of application in human ecology, safety, and textiles industries as well. And then what we'll do while those two heaters are firing simultaneously, we're going to monitor the temperature of that sensor coil by monitoring its change in resistance as a function of time. Um, and we plot that as a function of time in uh, terms of square root time. So the seconds to the 1/2 is the units on the x-axis here. And what that will do is give us a plot where we have an initial transient period, which is nonlinear, and then the plot becomes linear. And the slope during that linear region is directly related to the thermal properties of the sample materials. So it's the slope that we analyze to determine the thermal properties. So now that we've gone over the basics of the technique, we'll look at a few different application highlights. The first one is looking at some work out of Stony Brook University. It's looking at an exogeology type of application. This was from a conference paper entitled Thermal Inertia and Conductivity Measurements of Mars Analog Rock Samples. So specifically, this work was done to aid in the study of Mars geology and also to help characterize how Mars's atmospheric composition and its pressure is going to affect the thermal properties of especially the porous type of materials that you'll see on Mars, the sedimentary type of rocks up there. Uh, so in in these uh, NASA missions and similar processes, we'll often want to understand the thermal properties of the materials around that you'll commonly find on Mars in order to better design uh, things like rovers, but also in terms of designing for possible manned missions in the future. If you know, for example, that the soil on a Mars settlement has a thermal conductivity of a certain value that's much lower than the soil in on Earth, that might dictate the need to change thermal conductivity of the materials of construction to avoid excess thermal strain and to improve insulation efficiency, as one example. So what they did in terms of their experimental setup, on the right hand side, they have one of our pressure cell accessories, which they've called their Mars simulation chamber, which is a term I love. And so what they used this for was containing the sample in an environment that closely mimics the environment of Mars. So in this case, they're testing at pretty close to room temperature. But later on, they also have a thermal chamber to cool things down to temperatures that may be commonly seen in colder regions of Mars. Um, they also, because it's a pressure cell, they're able to, with the use of their vacuum pump and their vacuum pump control console, they're able to control the pressure inside of the pressure vessel to an atmospheric pressure more commonly seen on Mars. So in this case, they did a couple of things that they characterized. The first was looking at the thermal effusivity, what they've called the thermal inertia, to the porosity fraction of the rock sample. So you can see here that there is a correlation, although it's not perfectly linear. And that's because thermal effusivity depends on more than just porosity, but obviously, as porosity increases, thermal effusivity will tend to decrease. The next application page application highlight looks at the application area of geothermal heating, and this is from a conference paper titled Hydraulic Mechanical Characterization of Geothermal Reservoir Rocks. This was work out of the Helmholtz Center and TU Delft, as well as the Wuhan Institute of Rock and Soil Mechanics in the People's Republic of China. Okay, so in this case, the goal of the research was to characterize the hydraulic transmissivity of geothermal reservoirs. The hydraulic transmissivity can be poor for a number of reasons. One might be due to poor heat transfer properties of the reservoir itself, but also it can be due to low porosity in the reservoir, so fluid can't flow easily from one region of the reservoir to others. And in that case, it can be improved through modifying the porosity of the reservoir through the use of jets, which make lateral channels in the reservoir, which improve the porosity and therefore the hydraulic transmissivity. Thermal conductivity of the rocks in the reservoir are a key performance characteristic. Because it's directly related to the efficiency of the heat transfer between the reservoir and the fluid used as the heat transfer fluid in the geothermal application. So in this case, they had a number of samples which they had tested a variety of sedimentary rocks from various sedimentary basins. The first the first 8 or so samples on the counting from the left-hand side of this plot are sedimentary rocks. The third one from the right is a metamorphic rock, and then the remaining 2 are igneous rock samples. The next one is looking again at characterization of reservoir thermal properties, although in this case it's more of a fundamental science application. The idea is to generate data representative of different common sedimentary basins for use in a variety of different applications, mainly in the enhanced oil recovery and geothermal fields. So in this case, the sedimentary basins that they were looking to characterize include the Carpathian Fleischbelt, the Lublin Basin, and the Baltic Basin. And the idea is that, again, as I mentioned on the previous slide, that this data can be used to aid in hydrocarbon extraction process design or in geothermal process design. And I just thought a nice quote to take out of the paper was in the case of shales coming from boreholes, the size of the sample is rather small. Therefore, the TCI thermal conductivity analyzer by C-Therm Technologies in Canada was used, as it enables quick measurement of a small sample. So the TCI thermal conductivity analyzer is a device made by C-Therm, which uses the MTPS test method, and this just really encapsulates the benefits of the modified transient plane source method in characterizing these kinds of samples. And you can see the test results on this plot here. In this case, the basins, of course, most sedimentary rocks are laid down in a way that they're laid down in successive layers. And because of this kind of a layered structure to them, they inherently have anisotropy in their chemical and physical structure. And because of that anisotropy in their structure, they often have anisotropy in their thermal properties. So in this case, they looked at both the in-plane and the through-plane thermal conductivity of the rock samples. And you can see that all of the samples that were tested exhibited quite a substantial degree of anisotropy, and the MTPS method is able to very easily pick that up through a simple test on the rocks. The final MTPS applications that we're going to take a look at is taken from a paper published in Geothermics titled An Updated Ground Thermal Properties Database for Ground Source Heat Pump Applications. So, again, this is looking at geothermal heating applications. Um, this work is it comes from a rather large international collaboration from groups from ranging from Italy uh, to various other nations in the European Union, including Germany, as well as some research groups in Ireland as well. So in this case, the work that was done is specifically looking at shallow geothermal resources. So shallow geothermal resources are ones that are located relatively close to the surface, and they're quite attractive for use in residential ground source heat pumps, which are used for seasonal thermal energy storage to provide heating in wintertime and cooling in the summertime. If in in this case, the suitability of a basin for this type of application is really dictated by the thermal properties of the basin. If you have a higher thermal conductivity of the reservoir in the ground, you'll have a better efficiency of your heat transfer, and therefore better performance of the ground source heat pump system. So the next few slides are taken from work that was presented originally at the North American Thermal Analysis Society conference of 2017. We have these slides and this material courtesy of Dr. Eloisa DeCipio, who was one of the key collaborators on this work. So specifically, shallow geothermal resources evaluation, one of the things that you want to look at is the thermal conductivity values of rocks and unconsolidated materials that are characteristic of the basins that you're evaluating for exploitation in shallow geothermal resources type of systems. Um, and specifically, the goal of this work was to generate a regional database and a mapping of the thermal conductivity for these different geological materials in the different basins, in order to make a map of geothermal potential uh, for later exploitation in renewable heating and efficient heating. So, specifically, this is take taking a variety of different data sets and mapping them into a physical map based on where the samples were collected, and determining a factor of potential based on things like the average air temperature, the geothermal flux, as well as the thermal conductivity in the region, which could then generate a potential map of the geothermal exchange. So this slide is talking about how these kinds of sedimentary rocks and geological rocks tend to vary in their thermal conductivity. So you can see here, on the lower end of this slide, if you're looking on the right hand side, for example, looking at the difference between the volcanic and the sedimentary rocks, generally speaking, thermal conductivity of materials is going to vary as a function of its composition. One of the higher thermal conductivity minerals that exist is pure quartz, which has a thermal conductivity of around 7.5 watt per meter Kelvin. When you get into non quartz based minerals that are sedimentary, obviously the thermal conductivity starts to decrease considerably as you get into things, for example, like carbonates or shale type of materials. And as porosity increases and you get closer to a composition of air, uh, again, the thermal conductivity is going to decrease because air has a very low thermal conductivity of about 0.025 watt per meter Kelvin. On the left hand side, you can see looking at the difference between in composition in metamorphic versus plutonic and igneous type of rocks. So the difference between things like a granite type of material versus a quartzite and other types of materials. So the takeaway from these two triangle plots is that the thermal properties of a basin is really strongly dependent not only on its composition, but also its porosity and thermal history. So this plot is looking at the thermal conductivity of different rock samples from as a function of a variety of different variables. In the upper left, you'll see thermal conductivity versus porosity. Obviously, as porosity tends to increase, you will have thermal conductivity tend to decrease because the thermal conductivity of air and water is much lower than the thermal conductivity of most consolidated minerals. On the lower left, you'll see thermal resistance as a function of moisture content. Generally speaking, as moisture content increases, thermal resistance will decrease because the water is going to fill any pores, and water has a much higher thermal conductivity than air does. On the on the right hand side in the lower right there, you'll see the thermal conductivity as a function of temperature. Generally, for different materials, thermal conductivity will vary as a function of temperature, but how it varies depends on the chemistry and the physical structure of the material. Things like how crystalline it is, how pure it is, etc., will all affect the thermal conductivity relationship to temperature. So, in this case, they have a variety of different types of stones and rocks evaluated by the MTPS method. And in all of these cases, these are basically charts taken from a variety of different samples sampled in different locations. And you can get an idea of the spread of different thermal conductivity values of different types of rocks from different regions. In some cases, you can have a factor of 10 potential variation in a single type of rock, which is why it's so important to make sure that you're actually characterizing the deposit that you want to look at, because even if it's a well-known type of rock, its thermal properties might vary because the earth is inherently variable. Next. So, what they did was they took all of these data sets and collected them into this shallow geothermal exchange map, which basically plots the factor of potential versus the geographical area, and it shows the relative attractiveness for geothermal heat applications of different regions. In this case, pale yellow is relatively poorly performing, and bright blue is a relatively attractive region. So the next couple of application sets are using the Flex Transient Plane Source method. This is a double-sided bifilar spiral sensor, which you can see on the right-hand side of this plot. During a test, we heat that bifilar spiral sensor when it's sandwiched in between two pieces of sample and monitor the temperature of the sensor spiral as a function of time. And the behavior of the temperature response as a function of time is what lets us determine the thermal properties of the material. A variety of different sensor sizes are available with this method, which can be attractive if you're testing, for example, highly heterogeneous materials. You can use a larger sensor size to get on a larger effective sample size and test a sample which is more representative of the bulk average properties of the material. So yeah, as I had mentioned on the previous slide, in this case, when you're testing solid samples, you'll sandwich the sensor in between the two solid samples and then apply a heat pulse. We With this method, it tends to be a bit iterative in its application in that you run an initial scouting run based on your an estimate or an educated guess of the approximate range of the thermal properties of the material. And then you use the results from that scouting run to refine your test parameters. And you basically iterate in this process until the requirements for a good quality test result are met. And guidance on those requirements can be found in the ISO standard for this method, ISO 22007 2. So, one of the methods that, or one of the types of samples that the TPS method can be very attractive in terms of testing is porous geological samples like sandstone and pumice. Uh, the reason why this would be attractive for a TPS method in particular is that these materials are often very hygroscopic, which is to say that they tend to absorb water and other liquids. And as a result, they don't tend to be appropriate for use with a contact agent because the sample will just absorb the contact agent into its structure and the thermal properties of the material will tend to drift. Therefore, we recommend for these kinds of samples using the TPS method. Um, Another option that I've seen suggested elsewhere would be to use a transient line source sample. However, these samples tend to be very brittle, and oftentimes trying to drill the necessary guide hole for a transient line source sensor to be inserted could run the risk of breaking the sample. So, oftentimes for these kinds of materials, a transient plane source method is the optimal method for testing. So during your testing, you just sandwich the sensor in between two identical pieces of the sample. And you can see an example of this in this photo here, where we're testing a concrete as an analog of, for example, a concretion type of deposit, which you can find often in, for example, some volcanic tuffs. So we didn't have any volcanic tuff to test, but concrete makes for a good analog to this kind of a porous geological sample. And in this case, you can see the results from testing on 10 different regions of the concrete material here across 10 different measurements. In this case, the relative standard deviation of the tests is better than 3%. So as an example, and as a case in point rather of why you might want to directly measure the thermal properties of these kinds of materials instead of just taking a book value, you can think about the thermal conductivity range of pumice. Pumice is a commonly found volcanic rock. It's quite porous. And you can see that the typical thermal conductivity is going to range between a low of about 0.1 watt per meter Kelvin to a high of about 1.4 watt per meter Kelvin. And that's going to vary depending on the moisture content, the composition, and the porosity of the sample in particular. So, really, when you've got over a factor of 10 potential variation in this type of sample behavior, you really need to directly measure it in order to get an accurate number for evaluating whatever process you want to evaluate. Another commonly looked at porous geological deposit is sandstone. Sandstones are very common geological samples. Most of most anyone who has gone to uh, the beach has probably encountered a sandstone type of material at some point. I live in the region of Atlantic Canada, and in the coast along here, you'll see um, cliffs that are sandstone based in many areas along the coast. And these kinds of samples, their typical thermal conductivity ranges from a low of about 1.8 watt per meter Kelvin to a high of about 4 watt per meter Kelvin, give or take. Um, and again, the effective thermal conductivity is going to depend on things like the moisture content, the composition, the porosity, as well as in the case of sedimentary samples like sandstone, how well compacted they are. And for that reason, it really is important to directly measure them instead of just taking a book value. Another example is looking at volcanic tuff. Like pumice, this type of deposit can be sometimes very, very porous, and in other cases, it can be more dense depending on the nature of the process that created it. The effective thermal conductivity in this case can also vary by about a factor of 10, from a low of about 0.4 watt per meter Kelvin up to a high of around 4 watt per meter Kelvin. So again, when you're looking at a factor of 10 potential variation, you're really better off taking a direct measurement and knowing for sure what the typical thermal conductivity of the deposit that you're looking at is. The next set of application data we'll look at is the transient line source needle probe technique. So this technique is standardized for use in geological applications according to ASTM D5930 and IEEE standard 442-1981. When you're running a test, basically there's a inside of the needle on the probe, there's a heater segment, and you apply heat pulse to the line heater segment. And in our probe, we have two thermocouples, one of which is in the middle of the heater that's being heated, and the other is that way at the end of the probe. And the temperature difference between the thermocouple in the middle of the heater segment and the couple at the bottom of the probe is monitored as a function of time. And if we plot the temperature as a function of the natural logarithm of time, we'll get a linear region, which we analyze to determine the thermal properties of the material. So a common application of this needle probe technique is for testing unconsolidated geological samples such as gravels. So this is an example of the application of this technique to the testing of gravel. And in this case, it was a dry gravel, and we got an effective thermal conductivity of about 0.75 watt per meter Kelvin. Um, This technique can also be applied to testing of soils. So in this case, we're looking at application with ASTM D5334 and IEEE 442. So when you're testing according to the ASTM method, what's interesting is the thermal conductivity of the sample. And in this case, we looked at both dry topsoil, and we also added 50 weight% of water to determine the effect of the moisture content on the effective thermal conductivity. When you're testing according to the IEEE standard, the thermal resistivity is more interesting. So we uh, ran the calculation to determine the thermal resistivity both of the dry material and also of the 50 weight% water material. Uh, and so that sums up what I had to talk about today. I'll turn things back over to Adam, uh, and we'll open things up for the Q&A session.
Great. Thank you very much, Sarah. Excellent job, as always. We have just a couple of housekeeping items to share with you before we move to the Q&A session. So next week's webinar, we are featuring on additive manufacturing, and with a particular orientation towards more metal additive manufacturing, but we'll look at a range of different characterization tools applied in this space related to TGA, thermogravimetric analysis, DSC, differential scanning calorimetry, and of course, our core competency in thermal conductivity. We're going to be leveraging some of the work from our partners at C-Therm Instrumentation, world leader in thermal analysis and calorimetry, in this presentation. It should be a good one if you're involved or know of any colleagues that are involved in the additive manufacturing space. Do encourage you to check out that presentation. You can register at the link that will be provided in the chat box here shortly. We're also going to leave you with a couple of other resource materials for you to check out at your leisure. We're going to be dropping these links into the chat box. The first is the method selection guide. So Sarah and her colleagues have done a fantastic job developing a resource guide to know what it does is it brings together the theory of operation, the principles to these different techniques in a kind of common narrative in terms of understanding how they work and what applications are best where they're applied. So it's a free resource. I think it's about a 40 or 50 page guide book that's downloadable. And we'll provide a link in the chat box. I think Rose is dropping that in now. So do encourage you to check out that method selection guide. It can be really helpful in terms of, even just today, we've reviewed the 3 most prominent transient methods for thermal conductivity. But in this guide, for example, we also discuss some of the steady state methods, such as heat flow meters and other techniques such as laser flash, which can be useful for really high temperature measurements. So the method selection guide can be a great resource for your groups in the future. Another couple of links we're going to drop in here. The first is a video demo. So if you're looking at this and you're thinking, okay, this MTPS method or TPS or TLS were really interesting, but I'd like to just get a little bit better feel for what it's like to actually operate. What does it look like as it's running some of the materials? Of course, we had the video demo just before the short little video clip we played before the webinar. But if you would like to actually schedule a one-on-one session with one of our application specialists, we have a dedicated facility now set up with multiple cameras to run a live demo. And we have representative samples of all different types of applications. So if you'd like to schedule a video demo as a next step, this is a great resource available. There's no pressure. You can participate. You don't have to take it further than that. If you just want to learn more about the technique, you're welcome to do that. And we're happy to make that available to you at no charge. So the video demo link is in the chat box now. And then lastly, of course, you may be wondering what this costs. It is a modular product. It depends a little bit on what kind of needs you have and what budget you're working with. But we'd be very happy to provide a quick quote. If you want to the information and the link for the quick quote, this will get the ball rolling and we can provide that to you very quickly. I know a lot of groups, for example, are reviewing their year-end capital budgets and planning for 2021. And so just having some budgetary numbers available it may be helpful. Again, I want to stress we don't believe in any high pressure tactics here. It's simply for your information. If you're interested, we'd be happy to provide that to you accordingly. Yeah. Okay, so with that said, I want to thank Sarah for another excellent presentation. I want to thank Rosa for her help moderating the session, to Stuart Hillhouse for helping us organize it. I think we've got a number of my colleagues on the line as well. Our commercial director, Jarrett Nickerson, and some of our other representatives have joined us for this session as well. I thank them, and most importantly, you, the audience. Thank you very much for taking the time out of your busy schedule to spend with us this afternoon. We know your time is in high demand with all that's going on in the world, and really pleased to have this time with you. Okay, so with that said, I wish you all a great afternoon. Stay on the line if you wish to participate in the Q&A session, but we're going to move over to that at this point, and we'll stop the recording. Have a great day, everyone. Take care. Bye now.